Thank you very much. I want to thank the organizers for the invitation to give a talk. The meeting has been wonderful. I only have one complaint. I mean, the purpose of the meeting is to bring two communities. I was extremely happy until almost the end of Doug Arnold's talk, in which he showed the diagram of with greed for solving that equation motivated by Sorkin. And I saw with horror that he put the time axis in the horizontal direction. If you're going to bring the relativists together, time is always in the vertical direction. I was so shocked that I didn't have the courage to ask him what was the signature of the metric that he was using in his geodesic. For us, it's always minus, plus, plus, plus. So, okay. All right. So what I'm going to do is I'm going to talk about basically two components. One of them is an aspect connected to the formation of the final black hole when you had the merger of two black holes. And that one has potential implications, and the things that I'm going to talk, connections to gravitational wave observations and so on. The second part, what I say inside of the black hole, we will never be able to see that, of course. But nonetheless, what I want to show you is, given the modeling that we use in some of the simulations of black holes, just to see what happens after the two black holes merge, what's going on inside of that horizon. So just to start, so this is just to put things in perspective. I cannot believe that it's going to be almost 25 years ago since the first kind of large collaboration of numerical relativists worked together in what it was called the Binary Black Hole Alliance. There were some people that were not too happy with how it turned out. I think after 25 years, we mellow a little bit, right? And I think that it was a very important exercise, so to speak, to be able to have people with sharing a common goal, different approaches. Actually, some of the formulations, one of the ones that Doug talked about yesterday was one of the ones that we consider in developing those codes. There were many of them. But one of the things that I think came out of that is that people start realizing that the form of the equations play a crucial role in being able to ultimately come up with a code that is stable. We couldn't fully understand, but that was the first time in which we have a conversation with mathematicians. And that's how Doug and I met each other in 1992. All right. So here is another, by the way, so this is the merger of the head-on collision of two black holes. What you see there in green is the event horizon. The things in yellow, they are the photon generators. And one of the things that was very important in this work is that this part here is not smooth. It's a cusp. And that was why this paper made it to Science, in which there was an explanation of why we observed what we did. And actually, the first thing is that the numerical simulation that produced this came first, and then the explanation. All right, here is another example. When Bernd Bruckmann, who was at Penn State, moved to Jena, then started doing simulations also of, in this case, unequal mass black holes. So you can see here the event horizon of the smaller of them, and at the end, a merger. See some of the structure. Actually, some of this stuff I'm going to talk about it. How here again, time, and how this is the final black hole, and how it just settles down into what is likely to be a rotating black hole or a Kerr black hole. Here is another one, so you can see that the richness of this problem. It's done by Louis Leonard in the back, and the group in Pittsburgh. That's one he, was this part of your thesis, Louis? Yeah. And so that is the one in which you have white holes. So again, time in the vertical direction, and then you start with one, and then it just bifurcates into two. And again, here, the role in being able to model, being able to identify the horizon was crucial. And here is a simulation that we did in let me see. No, hold on. It's supposed to start at some point. That we did in Georgia Tech after the first detection. Why is it not doing this? I guess not. I hope it's not. And anyway, this was one of the simulations that we did just after the discovery. We were not the only one. Many other groups did. At that point, the machinery of numerical relativity was mature enough to be able to produce simulations that hopefully were close enough to what it was detected. All right. So the no? All right. So for this talk, as I mentioned, I'm going to divide it in two, but in between, I'm going to tell you how we model black holes. So the first one is what we call the approach to the final state. We had two black holes, each of them with spin, different masses. You can also have that there is most likely we will have zero eccentricity. That means they will be in quasi-circular orbits, but these days they have been an interesting game, which nature can produce maybe binaries in which you have a little bit of eccentricity. But anyway, at the end, what happens is that you have a black hole with just in which there are two parameters, basically. Astrophysically, we don't believe that the black holes are charged, but you have spin and mass. So you have seen this diagram before in this meeting. You have that when the black holes are separated, okay, you have that the signal is what we call a chirp. That is, there is an increase in amplitude, an increase in frequency as the black holes merge. And they merge, why? Because energy is extracted from the system via gravitational waves. In this regime, somewhere here, you can treat the problem with post-Newtonian theory. That is an approximation to the Einstein equations. And it does a reasonable job. There has been significant work on that regard. Then as you get closer and closer, and by the way, here for reference, this is when the separation is 5 gravitational radii, basically 10 m. And this is when it's 8. As you get closer and closer, post-Newtonian fails, okay? And that is when numerical relativity has to take over. And one of the crucial things, and we're having problem, is connected to the first thing that, the first conversation that Doug and I had was about initial data. And there's still a challenge to go from the post-Newtonian regime, in which post-Newtonian will provide you with basically the configuration, that is separation, orbital parameters, and spins of the black hole, and you feed that into the equations of general relativity, in this case the constraint equations, to be able to hopefully get initial data that represents an astrophysical configuration. I think that we were to some extent lucky, or maybe because we didn't know enough on that the naive approximations that we use, and most of them actually were from Jim York, in which you use a conformal flatness, that the extrinsic curvature is trace-free, and so on, that at the end, the errors that you introduced by doing that approximation, because it was not by physical grounds, it was just to be able to solve the equations, to simplify the equations to solve it. Those errors, so those didn't play a huge role later on when gravitational waves were detected. Why? Because still the detector doesn't have the sensitivity to look in exquisite detail those differences and so on, or the impact of that. All right, then numerical relativity takes over. You have a few cycles here that is taking that, and the signal keeps growing. At some point, the horizon, in case I'm going to elaborate more on that, the apparent horizons, you detect that there is one that is common and encapsulates the other two, or wraps around the other two. And the signal reaches a maximum, and then you have a decay that is a ring down. I will elaborate a little bit more on that. That is basically exponentially decaying sinusoidal. So you have seen this before. All right. What I'm going to focus is in this part here. OK. So the first thing, there are many, many paths to the final state. That is, given a black hole with a mass and the spin, you can envision several or different types of binary black hole mergers that lead to the same final black hole. Okay? And the question is, one of the things that I've been very interested in is, first of all, to get a sense of what that family of binary systems that lead to the final black hole is, and also to see how the binary has hairs, so to speak. It has, two spins, masses, orbital parameters. In principle, there are 17 of hairs. The interesting thing is to see how the binary is losing hair towards reaching the final black hole that only has two, spin and mass. So one of the things that a student of ours in Georgia Tech is doing is trying to explore that type of families that lead to the same black hole. I mean, here is one example in which it's just by brute force. What we have here is the situation of a binary system with aligned spins. Okay? And the only thing then you have to worry is the mass ratio of the binary system and the magnitudes of the not the magnitude, the magnitude with the direction of the two spins. So this is just a very rough, just to give you a sense of that, in which we had 3 different mass ratios, okay, and equal mass is 1, okay, and then for each of the black holes we just pick 7 different values of the spin, okay? And you have each color represents a mass ratio, and then you can see that you have 7 dots in each cluster, and then you have 7 clusters. So that is for each of the spins. And you can see here, for instance, this case or that case is giving you an indication roughly that you can have several, okay, that roughly give you the same final spin and the same mass. Okay. Actually, LIGO on the current sensitivity will not be able to tell the difference on that. You will have to do something else. So if you only see the last part of the signal. Okay? So this is something that we're currently doing. And after figuring out which ones give the same final spin, it's an interesting thing to see in the waveform, by looking at each of the modes, how each of the modes are, so to speak, damping or playing not a significant role. So at the end, all of the signals look very, very similar. Okay. All right. Now, let me talk about another aspect of approaching to the final state. So let me give you here an example. There is another binary simulation. It's equal mass. You can see that the separation is 6m. We use units of m, of total mass of the black hole is m. And there you have basically 1 or 2 orbits. This is the place at which this apparent common horizon appears. And here is a corresponding signal. In blue is this psi 4, and in black is just the envelope, the magnitude of that. Okay. Now this thing here, I purposely put this thing here, that is what is called junk or spurious radiation. And that is because of the approximations that we make to solve the constraints, okay? Mostly conformal flatness. And the reason is because when you assume conformal flatness, you cannot, I mean, let me just go back. Rotating the black holes are not conformally flat. I mean, you cannot find ways it's licensed to do conformal flatness. Nonetheless, we start with rotating black holes that in order to make the conformal space flat, there is this junk or spurious radiation that is introduced. But this thing here was also just to let you, people worry a lot. They say, oh, this is going to be, but for, again, the level of sensitivity that LIGO has, you don't have to worry about, except if you go to very, very, very high spins. And so far, nature doesn't seem to give us that level of high spins. Now, when we go in 2035 or 34 or whatever, when LISA, the space interferometer, flies, and they have a sensitivity in which the signal-to-noise ratio is of 1,000, then that thing is important. Okay? That thing will play a role. But we have time, 2035. Okay, so now one thing here, you see those dashed lines, okay? By the way, Doug, time in the horizontal, but it's not a space-time diagram, so I'm okay. All right. Okay. So as I mentioned before, you have a chirp. Here is very brief. But even before the signal reaches a maximum amplitude, that's when the common apparent horizon appears. And that's going to be important later when I talk a little more about this. then you reach a maximum amplitude, and later you reach a phase from here to the right, in which what we call is a quasi-normal ringing of the final black hole. And yes, for the purpose of what I'm going to say, quasi-normal ringing is just that the signal damped it's exponentially damped sinusoidal, in which there are these two constants. There are more modes on that. The important thing that came in the, I guess, the 70s or so, is that there is a connection between this frequency of oscillation and this damping time with the mass and spin of the black hole. That was found with perturbation theory. So this is important because if you find those two numbers, okay, then you can connect that to information on the mass and the final spin. Not only that, because you find different modes behave the same way with different values for omega and tau, those, if you find that they satisfy the values that GR tells you, okay, then you can actually say that these are black holes satisfying Einstein's theory, or what other people say is testing the no-hair theorem. Okay. So now, we have that. One thing that was interesting is that there are two things to fit here. One of these is the exponential decay, and the other one is this, the oscillatory behavior. So when you go and do from the waveform, if you go and try to do that fitting of the waveform to get these two quantities, the simplest thing is you separate the signal into amplitude and phase. So you do the fitting of the amplitude to obtain tau, and the phase to obtain omega. And what you find is the following. Here again is a place where the common horizon forms, okay? It's before the amplitude reaches a maximum. Here is the same thing here. And let's say this is where the student found that was the best point to fit this exponential decay. Here is the same thing, but doing a log linear fitting. So that is that, okay? And then if you go and do the fitting also, okay, if you go and do the fitting for the phase has to be growing linearly with t, and that is where the place where they found that the fitting for the phase. So the interesting thing is that, first of all, the common horizon, there's not, I don't know if it's strange, but the common horizon appears before the peak amplitude. Okay, just a few m before peak amplitude. Here is the common horizon. It's about 10 or so before amplitude. And the second thing is the quasi-normal ringing behavior of the phase shows before the quasi-normal ringing behavior of the amplitude. And as far as I know, there is no explanation for that. Okay, but maybe somebody here in the audience knows. And it's not. I mean, it is significant. So here is where the amplitude appears, and the other one. So, yes. Did you use only one breakdown mode, or did you also look at the overtones there? Because they, of course, became much faster. Right. And would be present in the early part of the we did every mode that we could in the simulation, and we found that the differences were different, but we found that, and now. Right. Yeah, but I mean, the thing is that there is some difference, and what I suspect, and this is my next, what is it? No, I have another slide for that. But what I suspect, it has to do with the way that if you go and look at these multiple moments of the horizon, if you use ABBA's, dynamical or isolated horizon machinery, then maybe from there you could find an explanation of why this is happening. Okay. All right. Another thing connected to that is the following. Okay, is that if you go and read the frequency of the gravitational wave at peak, so you go and read what the frequency of the gravitational is there, okay, and then you plot that versus the frequency of the quasi-normal ringing, okay, there is a correlation of the two. And again, if you go to this thing, even that there is a difference, all the quasi-normal ringing is after the peak amplitude. Okay. So we found a correlation between the frequency at peak, and in this case we put the final black hole, but remember, there is a correlation between the final black hole and the ringing of the black hole. So essentially this plot here is a relationship between the peak frequency here and the quasi-normal frequency there. Okay. And that again, I believe that the explanation has to be connected to these multiple moments of this highly distorted black hole and how things settle down. This is an observation. We just don't know why this happens. Now, it's not very tight, but I mean, it tells you something, okay? All right. So which is this, what I was just, as you approach the final black hole, okay, you can define mass multiples in the common outer horizon, spin multiples, and so on. And this is a paper in which you can look here in how, as a function of time, they decay. Because at the end, when you have a completely isolated, non-ringing Kerr black hole, all of them should go to zero, except, of course, the mass, and the spin of the black hole. All right. So I think they could be very interesting. I don't think you can do anything else with the numerical relativity, but just more delicate simulations. I think that now it goes back to the math side of things. People investigating how this occurred could probably shed some insights on that. Okay, so enough of that for approaching the final black hole. So what I'm going to do next is I'm going to talk a little bit about how we model black holes in binary black hole simulations, and then proceed to look inside of the final black hole. So again, just to put things in context, this is a single black hole simulation that we did in that binary black hole alliance. Look at it. It's here is the horizon. This spikes us because this is when the code was about to crash. You can see here by the size of the horizon compared to the box that the boundary conditions were basically at 3 or 4 M. And these were done in what at that time were supercomputers. Then, of course, in about 10 years, then you have the first simulations. France was the first one, and this here is a snapshot of the simulation that the group in Goddard made. So they had been with significant progress. So I'm going to just focus on how we handle the black holes. Okay? But before we do that, I'm going to remind you that we have been said here many times that the way we do this is initial value boundary problem. And I like to, when I give talks, remind people of how John Wheeler used to say geometrodynamics, that is the history of the geometry of space-like hypersurface. So you have two of those. This is the metric, intrinsic metric to this hypersurface. You have the extrinsic curvature that tells you about the embedding in the four-dimensional space-time. But the thing that I'm going to be coming back to this over and over during the rest of the talk is these two things, okay? So you had the freedom of picking coordinates, so to speak, okay? Or you had this gauge freedom. And that gauge freedom in this diagram is encapsulated in two things. One of them is the time that along the normal of the surface that you allow to get to the next slide, alpha, the lapse function, okay? That dictates, basically it tells you also about the proper time that you have between a point here and the next slide along the normal. But you also had the freedom of reshuffling or relabeling points. So if this P here is at this slice located here, there is freedom to be able to say, look, I want that this point here is what I'm going to call P. And that freedom is encapsulated by the shift vector. That's the one that you allow. And I remember when we were struggling as a community to figure out how to choose those two quantities. I remember hearing Richard Price, this is one of the situations in which too much freedom is not good, right? We just didn't have hint, but people work and develop different prescriptions and so on. And at the end, there were different ways to do it. Among one of them is connected to these harmonic coordinates that we talk connected to France's evolution. Okay, so let me, for the moment, focus on this alpha here, okay? So here is a diagram of the collapse of a star. So the star is the time in the vertical direction. The star is collapsing this way. At some point, there is a parent horizon that forms, and eventually, once that you have just the singularity, the parent horizon basically hugs the event horizon and that. But when we do the evolutions that we're marching in time, we're basically doing this foliation, slicing the four-dimensional space-time. And the thing that we cannot have included in the computational domain is the singularity. Okay. So one thing that we do is we pick slices in which we use the alpha function to slow down the passage of time. Yeah. So you can see here that time is basically proceeding at the normal stepping, so to speak, proper time stepping. But here, it's slowing down. Okay. Now, important to say that the slide that we label as t equal 150 here is everywhere here. So even here, the time, the coordinate time that you have there is 150. But if you start calculating proper time, you see that it's slowing down. We are avoiding the singularity. And that needed to happen also when we have black holes. Okay? Now, so here is the diagram that you find, the Penrose diagram that you find of a single non-spinning black hole. We leave here. This is where our visible universe is. Okay? So this is a spatial infinity, future infinity. Here is r equal 2m, that is the horizon. This is inside the horizon. This is the singularity. Okay? Of course, you have extensions of that. But let's just focus on the moment for this, because this is where we're interested. This is where LIGO is. Okay? And this is what we need to avoid. Oh, sorry. And this is what we need to avoid. Okay? We need to avoid this guy here. So we can do one thing. We can pick slicings like this. And actually, that is typically, as I will show you, if you do a Schwarzschild black hole and isotropic coordinates, and you can do the extension to do something like this. Okay? You can also say, well, okay, now let me go back. Let me go back for a second. We need to get inside, for the calculations, we need to get inside of the black hole. Okay? Putting boundary conditions at the horizon will be extremely difficult. First of all, you will have to track that event horizon. We cannot track it because you had to wait until future infinity to be able to say that where the horizon is. So you need to go to a region, safely inside the horizon, but not too close to the singularity. Okay, so here is one example of that. Another example is this, in which, yes, you go inside, but at some point, you truncate your computational domain inside of the horizon. You do whatever appropriate boundary or handling of the numerics there, and that's it. Okay? The other one is you do something like this. Okay? You can go, and you are avoiding the singularity, so to speak, by going all the way here to the intersection of future null infinity with the singularity there. So those three options, the last two are the ones that people have basically tried. So let's just show you what is called black hole excision. That is the one in which you go and truncate inside the horizon, you do the appropriate numerics and so on. These were the early attempts. People, they say, they still do it. Frank does it. The group in Cornell, Caltech do it. And, but just to show you how things started, this is a little bit of history, I guess. This is what we did in the Binary Black Hole Grand Challenge Alliance. And you can see here, it's an area where we had the apparent horizon. Just to remind you, if you find an apparent horizon, it's guaranteed that you have an event horizon outside. So we are inside the event horizon. There, you can see that it's all jagged. It has a Lego type of sphere because we're using Cartesian coordinates. It was a mess. Just the logic in that code to handle all different discretization stencils there, it was a mess in that code. And at that time, we were not generating that with Mathematica or the symbolic generation of code and so on. It was by hand. Okay. So here are examples. Actually, the one at the bottom was done by Ulrich Sperhacke that is here. Okay, he was at Penn State, was one of our postdocs. And it had some success. But the thing is, when the black hole is moving, I mean, you can see here the spikes behind. There is some trailing junk there. So it was not pretty. OK. So that's one approach. So for the singularity avoidance, remember the one in which you don't truncate, but you do this line. So one that I mentioned is you can just graph this. This here is the one that you get when, spatial isotropic coordinates. You can just then pick some way to evolve that in which you are creating subsequent slices like that. Okay. The problem is, of course, you have to go. Your domain also extends in the other side of the throat. It's not very efficient, but it's doable. And actually, there is a very nice paper by Mark Hannon and company that did just that. Okay. And here again, the trick is to find the gauge condition for alpha in which you are basically halting. You're stopping the evolution so you don't hit the singularity. Okay? That's why. And last but not least is the one that we now, at least half of the world uses, that is the moving puncture gauge. And in that one is the one that in principle you go, you avoid the singularity. You go to this point here. But of course, you effectively don't do that. You take advantage that we're doing things in a discrete fashion. And you're basically also truncating things here, so to speak. But the gauge, what it does is it basically slows down the simulation that all the slices go and pile up at the radius of our 3/2. Okay? So this gauge condition, and this is for the simple case you can find in this paper of a single of these black holes that are called trumpets, given the shape of the embedding diagram. And so this gauge condition is the one that is used for binary black holes, and it does the same thing. Okay. One of the things that I'm going to use in a second is the following. Is that in this evolution that also Mark Hannon did of this single trumpet, one of the interesting things is they plotted how the lapse function in the computational domain behaves as you get in this here, and indeed it collapses to 0. It tends to collapse to 0. And remember here, lapse collapsing to 0 is stopping the evolution on that region of space. I'm sorry? X. Remember, it's a single black hole, so it's spherically symmetric. So X is just a radial distance. This I don't remember at what time in the evolution. So which one of these corresponds? But yes, exactly. And this is how this shift vector behaves. But for the moment, I would like to focus on the alpha. Okay. All right. Okay, so now the last part is talking about inside the final black hole. All right. So before that, because I'm going to be talking about marginally trapped surfaces, apparent horizons, and so on, so some definitions. So let's say that sigma is one of those slices that we have in our numerical simulation, okay? And then you have a two-surface, S, okay? In that surface, you can define a normal to that surface, S, and then you also have the normal to the surface, sigma, okay? With those two normals, you can construct two null vectors, okay? K is an outgoing null vector, and L is an ingoing null vector, okay? So now, given all this machinery, you can then have the following. If this is the metric intrinsic to sigma, you can construct QAB, which will be the metric intrinsic to the surface S, okay? That's in terms of the, I'm sorry, that is not, this is not the metric intrinsic to sigma. This is the 4 metric, actually, okay? So that in terms of n and s is also given by that. Actually, the intrinsic metric to s is just this. I mean, to sigma is just this. This piece here makes it the projection in such a way that you have the metric intrinsic to s. Then you can define an expansion of k, the outgoing null direction, define it by this, okay? And you can also define the ingoing expansion, define it by that, okay? Where nabla is a covariant derivative associated with the metric G. Okay. The same way, you can rewrite this in terms of quantities that are in the surface of normal. So this expansion can be written in terms of the extrinsic curvature to this sigma, S, which is the normal to the surface S, the trace of the extrinsic curvature, and now this covariant derivative is the covariant derivative associated with this metric here. Anyway, now the important thing of this is that these quantities here, they only live in this surface, blue surface there. So, and that is quite convenient, because that's the way that we march to in doing our numerical simulations. That means that at any time during the evolution, we can compute these two quantities. We don't need the future, we don't need the past. It's all intrinsic to those surfaces. That is quite convenient, okay? So, what do we do with that? Well, then we have this situation that a trapped surface, okay, is one in which you have that the outgoing expansion is negative and the ingoing expansion is also negative. The marginally outer trapped surface is the one for which the outgoing expansion is 0, and this one stays the same. Then you also have a marginally inner trapped surface that is basically the other way around, and you have that. Okay, so these are, so what we have next is that an apparent horizon, okay, an apparent horizon is the outermost marginally outer trapped surface, okay? Remember, this is how you define a trapped surface. The expansion, the outer expansion 0, and the one negative inside. Okay? If you find the one that is the outermost of that, that is what is called an apparent horizon. Now, Abba Ashtaker and others had developed this machinery of dynamical and isolated horizons that are based in the definition of the dynamical horizon is just the world tube of these apparent horizons. Now, one of the things to keep in mind is that an apparent horizon is slide dependent. You can find, even if in a simulation you find an apparent horizon, in principle, in some instances, you can find a slice in which you don't find the apparent horizon that you don't find an apparent horizon in that slide, right? And I think, David, correct me if I'm wrong, Wall found a slicing in Schwarzschild in which you don't, in which you can find, in which you don't, All right, so this is what we have, okay? So we go find marginally outer trapped surfaces. We look for the outermost, and that is the apparent horizon. And then once that we find it, we know that we're safe. We can do everything inside because there is an event horizon outside. OK, so the other thing important to keep in mind is that there are these balance law. Okay, I copied this equation for one of the papers that Abba wrote, in which instead of mass, he wrote the areal radius of the black hole, in which said that the area changes due to mass energy going through or gravitational energy going through. The same thing here, the changes in the spin and so on. What I have on a plot here, sorry for the small labels, is the spins of the black holes, black hole 1, black hole 2, and the final black hole is called black hole 3, of two different simulations in which you can see that the binary system, the separation is large, the spin of the black holes, the magnitude doesn't change much. But as you get closer to the merger, then there is more angular momentum flowing through the horizon, and what you can see is that the spins actually change. All right. Okay. So now, let's just then go to this final part that I wanted to talk about, which is what happens inside. So this is what we have. In the spiral region, again, you have two parent horizons, or mods, in which in the surface you have, I apologize, in this slide, K is L and L is K. So what you have here, no, it's fine, it's fine. It's just that I have done it in another slide, but this is okay. So remember, at the surface, theta K is 0, and inside is negative. Okay, all right. And here, the same thing in the final black hole, because this is an apparent horizon, that is a mod. You have that, and the surface is 0, and inside is negative. Okay. So now what happens when the common apparent horizon appears, right? I mentioned that just before the peak, you have a common horizon appearing. So you still here have this situation in which at this surface you have 0, inside is negative, 0, inside is negative. Since this is an apparent horizon, you have that here, okay? You have that here, it will be 0, right? But then what happens inside of that? By construction, if this is, okay, a mod, which it is, you have that inside you have negative 2. So now you have negative expansion inside. You have negative expansion inside. So is this what you have? You have 0 there. And so you go negative 0 and go. That is unlikely, because then this will have to be, this region of space will have to be instantaneously changing from positive to negative. And that doesn't happen. So what happens is that you have what is called an inner horizon. So as the common horizon appears, you have this mods appearing, but you also have an inner horizon that is created at the same time. And that one evolves basically converting the positive region of expansion into a negative region. So now you have outside positive, 0, negative, 0, positive, 0, and negative. So this reminds me when I was studying these phase transitions in the early universe, where you have false vacuum and true vacuum, and each of the bubbles encapsulate true vacuum inside and outside, and as they merge, they convert false vacuum into true vacuum. So this is what you have. And a picture that perhaps helps to illustrate this more is from a paper of Eric Schnetter and company, in which you have here two black holes merging and spiraling. And this is the moment in which time runs in this direction. Okay? This is the moment in which a common horizon appears. And what you have is that the one that expands is the mods, or it eventually becomes a parent horizon of the single black hole. And what you see here going in, hugging this thing, is the inner black hole. Another way to put it, so this is the area of these two guys that are increasing in time. Then at this moment, you create both an outer horizon that grows and an inner horizon that shrinks. Okay? And it's seen in these snapshots of their simulation. So you have for instance, at this time, you already have it here in purple. You have the outer horizon. In green, you have the inner horizon. And in blue, you have the individual original horizons when the black holes were about to merge. And as you can see, as time proceeds, this green horizon starts shrinking and hugging the other two. Now, it's not that it disappears here. It's that the simulation could not find, I mean, the horizon tracker code that they were using could not find the horizon anymore. And that is very, very challenging to do, So Eric did some changes to this apparent horizon finder that Jonathan Thornburg developed many years ago. And they were able to push it a little further. Then he gave us the code, and we were able to even push the things a little further. And that's the last thing that I want to say. So what we did is, instead of doing binary in spiral evolutions that then it's a little bit tricky to handle the deformations and so on, we did head-on collisions, the simplest thing that you can. So here you have two black holes, again, time in the vertical direction, distance, in the horizontal. You have the two black holes, black hole 1, black hole 2, and these are this is the inner edge of the apparent horizon. This is the outer edge. You're going to say, gee, I mean, this thing is growing. It's just a coordinate effect. It's not the areas that stay put. Then you have at this time t, you have that an event apparent horizon common appears, and then the question is what happens after this. That was the thing that we were very interested in finding. So here's a comparison of, Eric also had head-on collisions. So here are a comparison of ours. Then you can see then, in this case, almost at the end of the simulation, we didn't see that these horizons were getting any close. I mean, they were getting closer, but also the surface, I mean, the shape of the horizon was shrinking due to coordinates effects. So we didn't see that they were merging, so to speak. On the other hand, Eric found that they actually merge. And here it is. They come together, they touch, and they cross each other. Okay. So we were really puzzled. Why is it that in his case they cross, and in our case they didn't? So we then explored the parameter space. Okay. The initial data was basically the same that Eric had and then we had. The only difference is that Eric and company started with the simulations in which they were already having a common apparent horizon within the two. So their simulations, the black holes had already merged, but he still had the two original black holes. So what we did is we said, okay, let's start moving them apart. By the way, we reproduce what they have. If you are inside, they merge. You start moving it apart, and if this is the separation, the original separation. This is the mass ratio of the two black holes. And we found that in this region here, if you start at this separation and with these mass ratios, these original apparent horizons of the black holes, they don't cross. They keep moving closer and closer, but the separation decreases exponentially, but their size, the coordinate size, also decreases exponentially. We were very puzzled about that. So, and here it is, okay? So I'm plotting here the separation of the horizons as a function of time. And this is for the case in which they cross, because we're doing log scale, the crossing occurs here, right? It goes, delta z goes from positive to negative. So this is the crossing time. And these are the separations, some of the one that Eric used and we have used. So you have the two cross, okay? And then they keep, now they cross and they bounce a little bit, they keep bouncing back exponentially. You see, this is a log linear. The other ones not. The other ones, they just go, this is again, this separation z, and there is an exponential decay in the separation. But if you also plot the radial size of this one, it also is exponentially, so they don't cross. So that was very strange, okay, until my student decided, well, maybe the problem is that we're plotting things in time, coordinate time. Let's just go and do it in proper time, which is, so what he did is that. He said, okay, let's first investigate what is the value of the lapse in the region where this thing is happening, okay, near the center of the final black hole. And he saw that in both cases, from now on, think about 0.7 cross, 2 doesn't cross. So this simulation, the black holes, the horizons cross. In this one, they do not. Okay? So the dashed line, this is the value of the lapse function, okay, for two that they don't cross, and look and see that it takes longer for the lapse to collapse. It takes longer for the lapse to collapse. And the other one, it collapses faster. Okay? All right? So this is also the value of the lapse at the origin, but as a function of this separation here. I'm sorry, as a function of the separation of the horizons. So you can see here that when the black holes, okay, are separated at that distance here, the lapse has not collapsed. You can just go straight across here, and the lapse has not collapsed. Okay? Then as it gets closer and closer and closer, they overshoot each other, and the lapse still has not collapsed yet. You see, just go from here, go straight here, and you can see that the value of the lapse. On the other hand, okay, at the same separation, okay, you can see here that for the large separation, the lapse has not collapsed there yet, but the separation is smaller. Okay. So the bottom line is that the reason that we see that for large separation they're done is because the gauge is such that it's slowing down the simulation. The proper time is smaller and smaller and smaller. Okay. We don't understand why the separation has an impact in one case and in the other one, but we know the reason why they don't cross once that you are in that case. And so here is the case in which they don't cross. Here is the case in which they cross. So here is the lapse function as a function of the separation of the horizons. And since we're using this gauge that is singularity avoidance, what is important to track is that if the lapse collapses, that is, if it goes to 0, there is an indication that hopefully there is a singularity that the evolution is trying to avoid. So this is initial data. Okay? So yes, there is a singularity here, and that's why the lapse collapses to 0, and here also to 0. Okay, so now let's see what happened in each case. Okay, so this is just one of the black holes. Okay? You can see that now the lapse is not collapsed. It's collapsing here because there is a final black hole, but here through all the evolution you have that the lapse has been collapsing. Hopefully what it means is that it's trying to avoid the singularity here, but here you don't have to avoid it because the lapse has already detected that there is a singularity at the origin. Okay? So it's all about this license here. And this is a little more difficult to see. So here is the lapse, the color of the lapse. Black is collapsing to 0. Yellow is going to 1. And that gives you a set. This is the plane, the XZ plane, just to give you a sense of what the lapse is doing. So you can see here that this one proceeds, okay, as the lapse already has collapsed due to the final black hole, and here one is still going on and on and on. Okay. All right, the last thing, let me skip this. The last thing is, what we did is we calculated this quantity, okay? That hopefully there is a better representation that there is a singularity inside, I mean, how the structure of the singularity inside of the black hole. But it's not quite, but it's probably better than the lapse. And here again, the one in the left is the one that results in a situation in which the black holes don't merge, the ones inside don't merge, and this one in which they overlap. And black is small, and yellow is large. So there you go. So this one, they remain disjoint, as I say, is because the lapse is slowing down the simulations of the black holes. All right, and last slide, okay, is the other thing that we found that was strange is that we track the areas of these two black holes inside the common horizon, and they grow, okay? Remember, you already have a single common horizon and the two inside. We don't have matter in the simulations. Okay? We don't have matter in the simulations. So the only other possibility is radiation. We don't have a way to calculate gravitational radiation inside of this black hole. So, and the estimates that we have here, okay, the estimate that we have here, we just don't know, not estimates, I mean the values that we just don't have a good handle of where this thing is coming from. Okay. Most of when you have a head-on collision, when they are, before you have a common horizon, you have a head-on collision, there is gravitational radiation going out. In the simulations that Eric has, he already started with the black holes already merged. The only radiation that he could have is spurious radiation for conformal flatness and things like that. So there is something going across the horizons of this inner horizon, but I don't think there is well understood what's going on. Okay, so just to conclude, I think we are in very exciting times in numerical relativity. There are many groups, different approaches, tackling different problems, alternative theories, things connected to LIGO, things with matter, and so on. And I think it will, I think we all agree that it's playing a very important role in understanding gravitational wave observations. I think that there is a lot of work that remains to be done. One aspect that Deirdre mentioned in the first talk that we're very, very interested in is I think our codes are getting a little old. We need to have new tools. But those are mostly the parts that are right now, some of us are concerned, is mostly with software engineering type of things, okay, for those codes at least. And I hope that I give you just some few examples of how numerical relativity could potentially be a tool of discovery for problems that are not just in astrophysics, but also connected to mathematical relativity, and something that was not mentioned in this meeting, but I believe also in quantum gravity. Thank you. Okay. Don't know. Don't know. Yeah. Yeah.
So, from the beginning of this workshop, we heard that in order to get well-posed formulations, you want to go to something like the harmonic gauge. And you're talking about the singularity avoidance gauge. So, those are two conflicting requirements. How do you bring those together with each other?
Well, as far as yeah, no, once that yeah, we're using, yeah, these simulations are done with this BSSM formulation and with the puncture gauge conditions for both the lapse and the shift, and there is nothing left there's no freedom left there. But now, maybe Oscar, is Oscar here? The analysis that Sarbach did with BSSN, that didn't include the gauge, right? This gauge. It did? It did. So
and there are papers also by Catherine Quintal and Maria Martin Garcia, and they treat exactly this gauge. It's strongly hyperbolic.
yeah. So yeah. Yeah. No. It does that by excision, right? The excision is precisely avoiding that. It.
It's really great that you have stuff inside the black hole.
Right.
However, I think this particular
definitely want to avoid the singularity. However, I think this particular gauge, like the trumpet slices, avoids the singularity by staying way away from it.
Right.
And so what you're mostly telling us is about the geometry of the limiting slice, not about the properties of the singularity.
Absolutely, absolutely.
However, harmonic time slicing also avoids singularities, but it gets arbitrarily close to the singularity, and therefore, has the potential to really tell us about what singularities are like. So, I mean, how tied are you to this particular way of doing things? Is there any way you can, sort of change the slicing to be more like harmonic slicing and get us a little closer to the singularity?
That's a very interesting point. I don't know if anybody has done BSSN with harmonic slicing. I don't know, but that could be a very interesting thing to do. Yeah. Has anybody done? David Brown was trying to. Okay. Yeah. No, it's. Yeah, but no. But I don't think it will be difficult, right? I mean, it could crash. I mean, the thing is, the analysis of the properties of the system is together, right? The evolution with the gauge conditions that you put. So I don't know what happens when you swap one with another.
But there are also some you need to calculate the contrast of slicing mechanisms that are powers used, which will make it less avoiding this. We intend on trying to avoid singularity. So that would
That is a good point. So the where is it? The gauge. Oh. Okay. So how close is, Franz, how close is this to the harmonic? There's a different power there somewhere, right? It's square, right. And so I don't know. I mean, we do have different powers in the code, so we can try it. I mean, here. In principle, in general, was an f of alpha there, right? Originally, how they start experimenting with that gauge. So you can probably pick it to mimic the harmonic.
But also, I mean, the fractional scalar really will tell you how close you are to the singularity, and even though it probably looks pretty big,
Yeah.
I'm betting you're not all that close.
Now, the thing that I don't know, for this, even that you're doing the very simple case of head-on collision, this is crucial because that's how we move these guys. So and this is not harmonic at all.
Well, the shift is not the problem. That just says how you move around within the slices.
Okay, so you're saying just to pick the harmonic, to pick the time part of the harmonic gauge only and forget about the other part.
Right.
Okay, I see.
If it's well posed.
Yeah.
You can't give up well posed.
Yeah. Okay, that's, sorry. Don't know. I mean, the way more than global, I tend to think. No, that's what we're doing here. I mean, that's what the gauge is doing. I mean, it's just locally slowing down in proper time evolution there.
Well,
Okay.
that's also what excision does.
Yeah.
Cuts out part of
Yeah.
now you have a whole with singularity.
Yeah. Luis? But I'm leaving. Can I just hear his question? Yes, that's okay. I think that's probably one of the things that is happening, Because now, the thing is that if you look at the metric inside of, if you look at how the metric inside of the common horizon settles down to whatever trumpet type of, I think that the differences are such that it's connected to what you're talking about. Yeah. All right. Thank you.